Okay, good morning, everyone. Can you hear me in the back okay with the mic? Okay, so before we get started today, does anybody have any questions over anything we've been talking about? Search engines, Google Maps, term paper? Okay, then just as a reminder, remember we'll have a quiz here in about an hour on our search engines unit. And also remember that the term paper is due today, tonight, 11:59. I know a lot of you have already turned it in. Awesome. To those of you that haven't, make sure it's in by tonight. We will start grading those, and then, like I said, it'll probably be the last week of classes when scores are posted for it, but we'll be working on it. But there's 115 of you, and there's 2 of us. It's going to take a little while. Otherwise, if there are no questions, sort of one more opportunity, then we will jump in. Okay, so the projector thinks it's Monday. I don't know what to do about that, but we'll deal with it the best we can. Questions? Okay, so then last time we were continuing our discussion of Google Maps, and we spent quite a bit of time looking at what it is that Google Maps actually does. How did Google Maps build this big database of all this geographical information? There were several articles that we summarized. I posted links to those articles this morning on Blackboard. Again, I strongly encourage you to go read them. They're not that long, and they're kind of fun, and there are some really cool graphics in them. But dealing with sort of combining all of these different sources of information, looking at satellites, looking at the streetcars, looking at user feedback in Google Maps, and how all of these different tools could be combined together to actually build this big database and catalog of all of these geographical pieces of information that then we can search when we're using Google Maps and trying to do route finding, perhaps. So, sort of where we left off last time then was coming back to sort of our driving question, and yes, the pun is absolutely intended. How do we determine the best route between 2 places? And so we put up this slide at the very end last time and said, well, there's basically 2 questions we're going to have to address first. One of them is, how do we mathematically describe our map? So we have now all of this geographical information. We have this map. How do we make heads or tails of it? And then once we've got that done, how do we actually define best? What do we mean when we say, what's the best route between 2 places? What determines best? Is there a unique way to do it? No, there isn't. And there can be several considerations that we might want to take into account. So let's start with the first question. How can we describe our map? So we now have all of these geographical locations. Maybe they're cities and we're looking at interstates that connect them. Maybe they're different, I don't know, where are all of the CVS's in New York City? It's going to be a pretty dense map. Okay, can we turn the sound down, please? Thank you. How would we describe our map? What do you think we might do? Happy Monday. Okay, well, we're going to get to an example here in a little bit, and we might just forego the projector today and do it on the whiteboard, but we'll get to that in a moment. How would we actually describe our map? Anybody have any ideas? What sort of tool might we use to describe all of these places and locations and routes? We could use a graph, right? So we could say, well, maybe all of the places we're looking at, whether they're cities or intersections, are what would they be on a graph? They would be vertices. These could be the places, these nouns, okay? And then what would be the edges between our vertices? What would be the relationship between them? What was that? Right, they could be roads. So is there a direct route between place A and place B? That's exactly right. And so, we could say these edges are, maybe they're paths, so they could be roads. Maybe if we're looking at airfare, there's a flight from, I don't know, New York City to Chicago. I don't think that's a stretch to assume that there is, in fact, a direct flight from New York City to Chicago, seeing as I've been on it several times. But we could come up with a graph that looks something like this, where now we've got, here are, 7 cities in the U.S., and we've got different roads connecting them. So, I don't know, maybe we've got I-80 here going from New York City to Chicago, I-95 from New York up to Boston, some combination of interstates from New York City down to Dallas, I don't think there's one that would necessarily get you in that direction. But is this a way that we can start now working with that map and trying to find routes and understand paths? Is this something that's going to help us? Yeah. So now that we have maybe a way for describing a map, okay, that question was pretty easy to knock out. Now we can come to our second question. How do we define best? Do you have any ideas? How would you define best? If we want to talk about the best route to get from, I don't know, New York City to San Francisco, how would you define best? Okay, so there are two factors that you raised. Maybe we're interested in what's the shortest distance. Okay, so we want to find the path that has the least number of miles or kilometers, if you're so inclined, between New York City and San Francisco. Certainly, we can do it. That's an objective function. We can put that together and say, given any route, what is the actual mileage that it requires? Okay, we could also then look, in most cases, this is what people are more interested in, is what's the least amount of time on a path. Correlates with mileage, but doesn't exactly line up, because different roads have different speed limits, there's traffic, there's construction, accidents, all those things. But maybe we could now have our function to say, well, if we want to know our best path, it's the path that takes the least amount of time. Okay? Is there anything wrong with either one of those ways to define best? No, they're both completely legitimate. So the idea here, as we said, there's no unique way to do best, but whatever metric we choose, we can start to associate a cost with the different edges. So let's assume we're looking at shortest distance. Maybe there's 191 miles between New York City and Boston on I-95. I have no idea if that's the exact length of I-95 between the two, but it's about 190 miles. Okay, and there's 722 miles from New York City to Chicago, 1,372 miles from New York City to Dallas on whatever that path is that we've taken. Do we now sort of have enough information that we could start to try to figure out what is the shortest path from New York City to maybe San Francisco? Sure. So when we think about shortest distance, what are we actually trying to do? Well, what we've ended up obtaining by looking at this map and all of this geographical information is, first of all, we get a graph. But secondly, we end up getting a weighted graph, because those different routes might have different numbers associated with them. They have a different length. They have a different amount of time. If we were thinking of maybe we were looking at, again, airfare or airplanes connections between these different cities, maybe instead we're going to look at the price of the ticket. That could be another way that we determine what's the best. What's the cheapest way to get from New York City to Chicago, or New York City to San Francisco, etc. And so we have this weighted graph that reflects this idea of however we're defining best. Okay? So our graph is weighted. Is it directed necessarily? Maybe not. Okay, was our graph on the last slide directed? Why not? Well, so in this case, if we're looking and supposing that these are just interstates connecting Chicago and New York City and all the cities, do the interstates run both directions? Yeah, and if it's 722 miles from New York City to Chicago on I-80, what's the distance going to be from Chicago to New York City on I-80? 722, I don't know, well, it could be 722.5 because there's always that median and there's the one direction's a little bit longer. But it's about 722 miles. And so we don't really have to worry about the directionality. If we were thinking about now airfare, and we were looking and suppose that these weights were the actual costs, so it costs, you must be flying Delta because it costs $722 to fly from New York City to Chicago. You know the acronym for Delta doesn't ever leave the airport? Anyway, that was a joke. Apparently it's too early in the morning for that. Okay. So would that necessarily lead to a directed graph if we were using airfare? Would it lead to a directed or undirected graph? It'd be a directed graph, because if it costs $722 to fly from New York City to Chicago, is there the guarantee that it's going to cost $722 to fly from Chicago back to New York City? No, we're not even guaranteed that there is a flight from Chicago back to New York City. Now, we know from common experience that there are, in fact, flights from Chicago to New York City. But the prices wouldn't have to be the same. So we might have to consider a directed graph if we chose our best metric to be a little bit different. In the case where we're just minimizing mileage, it doesn't make that big of a difference. And we can just have an undirected graph. Okay? And then the last thing, thinking back to our organ donation unit, so we've seen our graph is weighted. At least in this example, it's not on the screen, but it's undirected. Is it cyclic? Are there cycles in the graph? Sure. I mean, we can see there's sort of 1-3 cycle between New York City, Chicago, and Dallas, New York City, Chicago, and Boston. We could find 5 cycles. We could even find a 7th cycle from, like, Boston to Chicago to Denver to San Francisco to LA to Dallas, back to New York City and up to Boston. Okay? It's displaying just fine on my lectern up here. We'll make do. Okay. So we have this graph. We have this weighted graph. Okay? And what this idea of best is coming down to is that we've set up some sort of cost function. So think back to our search engines unit that we had a little while ago, where we could have different algorithms. We had a cost function. However, we were measuring algorithm performance. Maybe it was looking at the actual number of operations. It was the number of comparisons. We might have looked at the amount of memory the algorithm required as it scaled with problem size, but there was a cost associated with increasing problem size. In a very similar way, when we're thinking about now these maps and looking at directions, there's a cost to using any edge on the graph. And this is how we get at this idea of best. However we define best route, that determines our cost function. And so maybe for the graph that's sporadically displayed on the screen here, what those numbers are showing, that's our cost function. So there's a cost of 722 to go between New York City and Chicago. Contextually, we might say that that's miles. But generally speaking, when we're looking for the best route with regard to distance, do we want the highest distance or the lowest distance? Typically want the lowest distance. And so we can start to put all of this together to see how do we go about trying to actually find that. Okay? And just as we had with algorithms, there's no unique way to measure the cost of an edge. As we've said, it might be just literally how long is the path? It was 722 miles. How long does it take to traverse the path? I don't know, it's about a 10, 11-hour drive to get from here to Chicago, assuming good traffic and good weather. Okay? But that's something we could take into account, and we could redefine our cost function to look at time instead of distance if we so chose. And so once we've taken this question, how do we find the best route between 2 points, and sort of develop this mathematical model where we have this weighted graph and all of that, what it comes down to from a mathematical sense is we're now trying to find a path in the graph with the desired endpoint. So again, if we say we want to find the shortest path from New York City to San Francisco, and Google Maps tells us how to get from Chicago to Dallas, is that really all that useful? No. Doesn't matter if it's the best route from Chicago to Dallas. That's irrelevant. Okay? So we're going to have to make sure we have those desired endpoints, and that has minimal cost. That's what we're actually doing, and how to translate sort of this real-world problem from Google Maps into something that we can now sink our teeth into. Okay? Any questions on sort of this setup? Okay. Then the way that this works, so I know there's a lot of text on the slide here, but we'll work through a big example here, is there's an algorithm called Dijkstra's algorithm. I know it has sort of a weird spelling. It's pronounced Dijkstra. And so what this basically does is try to find shortest paths through graphs with a specific starting and end point. Okay? So we're going to do a developmental example. We'll work through it in a couple slides here, where we're going to use that map of the U.S. we've already seen, and we're going to try to find the shortest path from New York City to San Francisco. Okay? So now we could go back to this map here, and if you were to look at this, as a human being sort of looking at this, is it that hard to figure out the shortest path from New York City to San Francisco? You're probably going to use your intuition to know that New York City and San Francisco are approximately the same latitude, so we're probably going to want to go as directly west as possible and not have a lot of north-south, and you can probably piece it together pretty quickly by looking at this map. But could you, in principle, have a map that you have absolutely no intuition for? Yeah. You'll find on the homework assignment when I post it this weekend that we'll have a wonderful map with places like Hogwarts and the Shire and all sorts of other list of fictional places. And maybe you want to find how to get from Hogwarts to, I don't know, the Shire. I forget what else I have on the map. But something that you have no intuition for whatsoever. But this algorithm will work just fine. So the idea of Dijkstra's algorithm, then, is it takes an arbitrary map. We don't have to have intuition. We don't have to have an idea of sort of what that shortest route is when we start, but we can still figure it out systematically by going through the graph and applying some operations. So first of all, we see that it's an algorithm. Okay, so we're going to have to sort of bring our search engine's hat with us and start to think, how does this algorithm work? What are these step-by-step procedures that we're going to need to follow? We'll talk about the scaling of this a little bit later when we finish the example. And so to dive in, the steps that we're going to need come in a couple flavors. So there's a few things we have to do just to get things started. There's a sort of a setup cost when we start running Dijkstra's algorithm. And so what we're going to have to do is, first of all, keep a list of all of the vertices we visited. The idea here is you can think about, we've got a car, and we're going to move this car all around the graph from vertex to vertex, and sort of keep a tally of where all have we visited and what are the possible places we could go next. Okay? So to do that, we need to do a little bit of setup. So we're going to have to determine, have we already visited a particular vertex? Okay? So naturally, in the beginning, we want to try to get from New York City to San Francisco. Have we visited any of the vertices? No. Okay, maybe we'll assume, as sort of the last sentence on point 1 here has, we'll assume maybe our car is at New York City. We're at our starting point. But have we, at least from the terms of this algorithm, have we visited any of the other cities? No. So we need to note that, to say, well, we're in New York City, but we've not visited Boston or Chicago or Dallas or Denver or any of the other cities that were listed. And then what we're going to do as we work through this algorithm, starting to get set up here in item 2, is we're going to track the shortest path as measured by that cost function through the weights in our graph from New York City to any one of the other vertices. Now, as we're working through Dijkstra's, this isn't necessarily going to be the cost of the shortest path. This will be the cost of the shortest path we've seen so far, with the idea being that by the time we finish the algorithm, we will have, in principle, looked at all possible combinations. It turns out we won't look at actually all of them. We can do things a little bit more intelligently. There would be some redundancy if we looked at all of them, and we don't like redundancy in algorithms. But with the idea that by the time that the algorithm has ended, whatever those shortest distances that we've seen so far are actually our shortest distances. So as we're running through, at any point in time, what we call the shortest distance may not actually be the shortest. It's just the shortest one that we've encountered up to that point. But that's the idea of the algorithm, is looking for other paths. Is there a shorter, is there a better way to get there? Okay? And so to start, if we haven't actually seen a path, so again, all we know is we're in New York City. We don't even know where can we go next, because we haven't actually looked at the graph yet. Okay? So we haven't found a path to Chicago. We haven't found a path to San Francisco. So a convenient starting point is to say, well, the shortest path that we've seen so far has a cost of infinity. Because is any tangible path lower in cost than infinity? Yeah. So that then flags, well, the moment we see a path, that's better than no path. Okay? So that's the startup. So what we'll have, we have our map. We're going to start to see, this map is going to be redrawn on a lot of the slides. We're going to introduce a table up top here to sort of see what are the cities that we visited and what are those minimum distances. And I guess maybe now's probably a good time to put that up. Okay, so, and the projector's even working. Behave. Okay, so what we're going to see on these graphs as we work through, our current location, so wherever we can think of our car being parked, is going to be displayed in red if the projector is working correctly. And we'll have up here, here's again this table, so here's our 6 other cities. Naturally, what's the shortest path from New York City to New York City? 0, just stay in New York City. So do we really care about that particular thing? No. So if we were already in New York City and that's where we wanted to go, we wouldn't be going through all of this hullabaloo. So notice New York City is just omitted up in that table just because we don't really care about it. Okay? And so naturally, we haven't started looking at any of the paths yet. We haven't looked at any potential paths. And so we have no idea how to get to Boston or Dallas or LA. We haven't seen a way to actually do it yet. Okay? But there's our setup. We put our person in our starting location, and we say there's an infinite distance or infinite cost to all of the other locations. Everybody still with me so far? Okay. Once we get past the next slide, we're probably just going to move to the board because this is getting a little ridiculous. Okay, so now, how does Dijkstra's algorithm actually work? Okay, so now that we have this startup complete, we're going to enter into a loop. Okay, so we're going to go through all of the vertices on the map one by one. We're going to do it in a particular order that will be determined as we execute the algorithm. But we're going to have to consider all of the vertices one at a time. So we get this big loop. So what we're going to do is we're going to say, suppose we're at some vertex. That's where our car is parked. Someone had to stop and get a Portillo's hot dog in Chicago. Okay. What we're then going to do is we're going to consult our map, looking at our graph, and say, well, what are all of the places we can go from our current location? Which is to say, look at all of the outgoing edges. What are the other vertices we can get to? Okay? And so what we're going to do is then consider what are those hypothetical paths. If we know there was a cost of, I don't know, so we're in Chicago. There was the cost of $722 to get from New York City to Chicago. And we know from Chicago we can get to Boston. And that had a cost of like 800 something on the slide. So this now hypothetical path would say, go 700 some miles from New York City to Chicago, and then another 800 some miles from Chicago to Boston. Well, that produces a total path of length, or of cost, 1,500 some, to get from New York City to Chicago, or New York City to Boston. And we ask ourselves, is that the shortest path we've seen to get from New York City to Boston? If it is, then we're going to make a note of it on our table. If it isn't, what are we going to do with it? Do we actually care about that path at all? No, we're just going to ignore it and move on. But that's the idea then. So we'll look at all of the outgoing edges at our current location and consider all of those hypothetical paths. If any one of them is better than what we've already seen, we'll store it and keep it for later. And if it's not, we'll just move on to the next one. Once we're then done looking at all of those outgoing edges, there's really nothing left to see at that city, and we have to make a determination. What's the next place that we go? So we'll look at our total list of all of the cities. We'll ignore the ones that we've already visited, because if we already know how to get to Boston, is there any point in going back to Boston later? No. And we'll say, well, what's the city that now has the shortest path from New York City that we haven't visited? Because now we know that's going to have to be the shortest path. Any other way, if we find it later, is going to have to be longer than that, because we would then have to go to a city we haven't visited yet, which has a longer distance, and then we would add more cost on top of that to get back to whatever that city is, which is just a longer path. Okay? And so we then move our car to that city and repeat the whole process. This does get rather tedious and repetitive very quickly, which is why we will not have remarkably long examples here or in the homework. But that's the general idea. Okay? And then on our way out of the city, so as we're leaving Chicago, we mark that we have, in fact, visited Chicago, and we move our location. Okay? That's the general approach. Does anybody have any questions on this right now? And we'll certainly work through an example here momentarily. Okay. So, at our starting point, we're in New York City. I don't know, we'll see if the projector can hold out here. Okay? And so, we have our current location, New York City right there. Fine. We will copy our map onto the board. Apologies to those of you listening at home. And then we will turn the projector off. Okay, so we had San Francisco was here. Have LA down there, and that was 349 distance. Denver was here. There was a 925 from San Francisco. Let's see, and then we have Chicago. From Denver to Chicago was 908. And from Chicago to San Francisco was 1855. All the way over here, we've got Boston. Boston to Chicago was 860. Is our New York City. There was 191 from there to Boston, 722. And then last we've got Dallas down here. And Dallas had, what was it, 1235 to LA, 645 to Dallas, 798, excuse me, to Chicago, and a 1372 to New York City. Okay. All right, everyone can see that okay? I apologize. The slides will be posted after lecture. Go look at them there. Okay, so what we're going to do is make now our list since we don't have the lovely table. So we'll say we've got New York City, we've got Dallas, we've got Denver, alphabetically next to Chicago. That was a joke. Boston. I've already got Denver, LA, and San Francisco. Okay, so we've got all of these. We know presently we're in New York City, so we can just sort of check that off. Or actually, instead of checking off, let's put an arrow there just to denote that's where we're currently at. And then what we're going to do is we can keep a big table here and say, well, what's our minimum cost so far? What's the minimum cost path to New York City that we've seen so far? Just 0. Okay, again, we don't really care about that case, but for completeness, we can put it in. And what's our minimum cost to get to any of the other 6 cities from our setup? We can think of it as infinity. We haven't actually seen a way to get from New York City to Dallas, or New York City to Denver, and so on and so forth. So we can put a whole bunch of infinities here. Again, just as a placeholder to say we haven't actually seen a path. And then one other thing that we'll track, this shows up nicely in the slides, but since we don't have that, we'll use another thing, is we're going to track on whatever the shortest path that we've seen so far, where did we come from? So naturally, the shortest path from New York City, we came from New York City, but again, no one really cares about that. And since we haven't actually seen a path to Dallas, we don't know where we were coming from because there isn't such a path. Okay, everybody still with me? Okay, so first thing we're going to do, knowing that we're in New York City, is we're going to want to look at all of those outgoing edges, because these are now hypothetical paths. We could move from New York City to Boston. We could move from New York City to Chicago, and we could move from New York City to Dallas. Okay, so we can go through each of those lengths, or each of those paths. So suppose we took the New York City to Boston path. That tells us we have a path to Boston, because that would be our ending point. And what is the total cost of that path from New York City to Boston? Well, it's just 191, because does it cost us anything to get to New York City? No, that's where we started. And so we add 191, so we see that there's a path of 191 to Boston. Is that cheaper? Is that lower cost than the already best path we've seen? Yeah, we haven't actually seen a path, but certainly 191 is less than infinity. Okay, so we can put in a 191 here, and sort of updating our path now. On that path, where were we immediately before going to Boston? We were in New York City. Okay, so we can annotate that. That way we know later when we want to read this off, well, if we want to get to Boston along this path, we come to Boston from New York City, and we come and say, oh, well, New York City was our starting point, so we just go that route. Okay? Likewise, we next consider our New York City to Chicago path. That gives us a total cost of $722. Is that better than the best path we've seen to Chicago? Yes, it is. Okay, so we update our table. We've got a 722 there. And again, where did we come from as we went directly to Chicago? We were at New York City again. Okay, and then lastly, we do the same thing for New York City to Dallas. We get a path of 1372. Is that better than what we've seen to Dallas already? Yep. And so we fill out the table. Are there any other outgoing paths from New York City that we need to look at? No. Okay, so this now sort of brings us to the end of this step of the loop. we now will say, well, we've visited New York City, so we remove that arrow and we can put a check. And now we need to figure out what's the next city that we go to. Okay? So we look at our table and we find the unvisited city, so we're going to exclude New York from a consideration, that has the shortest path so far. And so we look 1372, infinity, 722, 191, infinity, infinity. The Boston at 191 is the closest city. That is the shortest path that we haven't visited yet. So that's where we now put our location. We're now going to sort of move our car up to Boston and examine what happens next. Okay, so we've now moved up to Boston. Everybody with me still? Okay, and we're going to do the same idea. Let's look at all of the outgoing edges from Boston. What are all of those paths? Well, how many potential paths do we have leaving Boston? We've got two. We can go to Chicago, or we can go back to New York City. Are we even remotely interested in going back to New York City? No, that seems counterproductive. And of course, we could still consider this. So there's a cost of $191 to go from Boston back down to New York City. Well, there was a cost of how much to get to Boston in the first place. $191, because we had to go from New York City up to Boston and then back down. Well, that would give us a path of, what would it be, 382? I think. Is 382 the best path we've seen in New York City? No. We had a 0, so we would automatically exclude it. You can consider it if you want, but you can just sort of ignore any of the vertices we've already visited when you're looking at these outgoing links. Okay, so we don't care about the one going down to New York City, but we can also potentially go from Boston to Chicago. Okay, so if we add that, that's a path of 860 costs to get from Boston to Chicago. What is now the total cost of that path? If we were to go from New York City up to Boston and then over to Chicago, what's the total cost of that path? I get, what is it, 1051? Okay. Is that the best path to Chicago that we've seen? No, it isn't, because we've already seen a path of 722. So do we care about at all going to Chicago from Boston? No, that's just stupid. That's expensive. Okay. So as it turns out, did we actually update anything on our table by going to Boston? No, but we've now convinced ourselves that unless we're going to Boston, we have no business going to Boston. Okay? So we've finished that iteration of the algorithm. We can now mark Boston as a visited city. And so now we need to figure out where's the next place that we put our little vehicle as we're considering the graph. What do you think it's going to be? We're going to go to Chicago. So again, we want to come and look at all of the unvisited cities, so Dallas, Denver, Chicago, LA, San Francisco, and look among those which has the shortest path from New York City. Because as we've seen, if it's now Chicago, is there any shorter way to get to Chicago? No, because if we left New York City, we could have gone through Boston, but that was more expensive. And if we leave New York City and go through Dallas, well, just to get to Dallas is 1372. There's no way we can get to Chicago faster than 722. Okay? So we'll say now Chicago is our new home for the time being as we're working through this algorithm. And so now we have to ask ourselves, and as we go through this same procedure, what are all of the possible paths we can take leaving Chicago? How many are there? I see 5. Okay, so sort of let's work clockwise. We can go from Chicago to Boston. What is the total length of that path going then from New York City to Chicago up to Boston? Well, so there's a cost of $722 to get from New York City to Chicago. We add on top of that 860s. That gives us what, like 1582, I think? Is that the best route we've seen to get to Boston? No, that's way longer than the 191. So do we care about that path? No. But again, we could have already known that. We've already been to Boston. So we could have just sort of excluded that one. Likewise, do we care about going back to New York City? Nope. Fine. So let's look down at Dallas. So we now have a proposed route where we would get from New York City to Chicago for a cost of $722, and then down to Dallas for a cost of $798. So that gives us what? I think it's $1520? $1420? $1520. Yeah. Am I doing my math right? Okay. So we now have a proposed path to get to Dallas of cost $1520. Is that the best path we've seen? No. So do we care about it? Nope. Moving on, We can get from Chicago to Denver, okay, and the total cost of that path is going to be what? I get 1630. Is that the best path we've seen to Denver? Yeah, because we haven't actually seen a path to Denver yet. So, of course, this has to be the best one we've seen so far. It's the only one we've seen. Okay, so we can update our table. We now know there's a path of distance 1630. And what is the city on that path immediately before Denver? It's Chicago. So the way to sort of think about this notation, if we now wanted, suppose we're done, and this is everything finalized. Of course, we're going to still keep working here for a little bit. If we wanted to know our shortest path to Denver, we would say, well, to get to Denver on this path of 1630, we came from Chicago. And Chicago, we came from New York City. And so you can then sort of track what is the route, sort of working iteratively backwards. Okay? So that's cool. And our last outgoing link from Chicago, where can we go? San Francisco. And what is the total cost from New York City of that proposed route? Yeah, I get $25.77. Does that seem right? Okay. Is that the best route we've now seen to San Francisco? Yeah. So we come down here, we update our table. You get a $25.77. And again, that was coming to San Francisco from Chicago. Okay. Are there any more outgoing links in Chicago that we have to consider? There are? Okay. So we're done with all of those. So what that's saying is it's time to move on. We can mark Chicago as visited, and now we have to figure out what's the next city we're going to consider. So we look at all of our unvisited cities, and which one has the shortest path, total path from New York City? Well, Dallas is potentially it at 1372, Denver at 1630, Los Angeles at infinity, or San Francisco at 2577. Which one do we want? We want Dallas, right. So we move our location to Dallas, and we repeat the procedure all over again. So how many outgoing links are there from Dallas? There's 4. At least I count 4. Okay. Do we care about the ones going back to New York City or Chicago? No. We've already been to those cities. So there's 2 of interest. We've got one up to Denver and one over to LA. So let's do Denver. What's now the total cost of New York City to Denver, assuming we go through Dallas? Okay. Well, sorry, what was it? 2017, yeah, that looks about right. Because we had, to get to Dallas was 1372, direct from New York City. We added that to 645, and yeah, that gives us 2017. Okay? So is that the best route we've seen to get to Denver? Nope, we don't care about it. And so lastly, we have this outgoing link to LA. What's the total cost of that path? 2607? Somewhere around there? Is that the best path we've seen to LA? Yep. So we add that in, and that was coming from Dallas. Okay, so the cool thing now is we now have a path to get to every city. We at least know New York City and LA are connected, despite what New York City and LA might think of each other. You can't actually get from one to the other. Okay? So, anything else to do while we're visiting Dallas? I mean, probably stop and get a steak, but that's not part of Dijkstra's algorithm. Okay, so we mark Dallas as visited. Now which city do we go to next? We have 3 unvisited cities. We've got Denver, LA, and San Francisco. Which one has the lowest cost in total? Denver, right. So what this now tells us is that this path from Chicago that totals 1630. Again, this is now the total cost from New York City. This just tells us what vertex was immediately preceding it in the path. Had a cost of 1630. And so we can look at all of the outgoing links from Denver to consider potentially new paths. How many outgoing links are there from Denver? I see 3. How many of them do we actually care about right now? Only 1. Why do we not care about Chicago and Dallas? We've already been there. So we see that Denver has a path up to San Francisco. And so now what we have to do is we can consider that path, which says we know how to get from New York City to Denver, and that has a cost of 1630. We're now going to tack on an extra step to say we can get from Denver to San Francisco with a cost of 925. So what's the total cost of that path to get from New York City to San Francisco? What is it going to be? 2555? Something like that? Okay, so we now have a proposed route of 2555. Is that the best path we've now seen to San Francisco? Yeah, it is. So we update our table. We clear out this one that said, well, we could get to San Fran from Chicago. That's no longer the best. We put in our new cost, 2555. And what's the city immediately preceding San Francisco? It's now Denver. Okay? Is there anything else to do while we're in Denver? Okay, we went skiing, but we're done with that. We're back in the car. We're moving. Which city do we now visit next? We visit San Francisco. Okay, so now, from an efficiency standpoint, this now tells us, because we're in San Francisco, this is the shortest route. And were we looking for, what were we looking for when we started this example? The shortest route from New York City to San Francisco. So at this point, we could stop, because we know we're not going to do any better than this. We actually don't care what's the shortest path to LA. We're going to work this all the way through just to show how everything will work, but we could stop here if we wanted to. What is that shortest path to San Francisco? Well, we know it has a cost of $25.55, and to get to San Francisco, we first came from Denver. To get to Denver, we came from Chicago, and to get to Chicago, we had New York City. So it's New York City to Chicago to Denver to San Fran. That's our shortest path to get from one to the other. Everybody with me? Okay. So continuing our example, suppose we just wanted to go all the way to completion. We're now in San Francisco. How many outgoing edges are there? There are 3. How many do we care about? Just the one. We've already been to Denver, and we've already been to Chicago. And so we know that we can get to San Francisco for a cost of $25.55. And on top of that, we could add a cost of $349 to get to LA. So what's now the total cost of this proposed route to Los Angeles? What would it be? $28, $29.04? $29.04, I think? Okay. Is that the best route we've seen to LA? Nope, so we don't care about it. Anything else to do in San Francisco besides ride the monorail? Or the trolley, rather. You know what I was thinking of. Okay, and so lastly, we go and we visit LA. Are there any outgoing links that we care about? No, so we're just done. Okay. Are there any other cities that we need to go and visit? Nope. So what we now have working through this is not just the shortest route to San Francisco, we actually have the shortest route to all places on the map. If we wanted to know how to get from New York City to Dallas, well, we can just read through here. Well, Dallas, cost is it's $13.72, and just take the direct route from New York City. Okay? And so, in this sense, we certainly got our answer to San Francisco, but we actually got quite a bit of information more as well. Suppose now, instead of starting at New York City, we wanted to start at Denver. We want to know how to get from Denver to Boston. What would we have to do differently? Or how would that work? Right. So we would start off when we were setting up our function. So everybody's got this table. We're not going to do this whole example, but we can just sort of work what would be a little bit different. So in that case, if we were starting from Denver and wanting to get to Boston, when we did our original setup, well, we would know there's now a cost of 0 to get to Denver because we're already in Denver. And then what are the other costs to all of the other cities at that starting point? They're infinite because we haven't actually seen any paths. So we could fill in our table like that. And then basically go through and do these steps over and over and over again. And so we would consider how many outgoing links are there to Denver? What paths do those tell us? Are they better than the ones we've already seen? Okay, which city do we then move to next? And go do the same thing. And once you complete the whole table, you would then find what's the shortest path from Denver to any of the cities in the graph. Okay, but we don't necessarily need to work through that. So let's try the projector again. see if it's going to be more behaved if we turn it on a second time. Okay, so as we've gotten the slides, so just to sort of summarize what we did, so again, we have sort of in red here is where we were visiting, and as we go through here, we saw, so New York City is now green, we've been there, we updated our table, we go to Boston, Chicago, and you're noticing that that table is getting updated with what we saw on the board. Everything's summarized in here as we sort of move from the cities. And I think we did our math wrong. We should have done LA before San Francisco. You get the picture. Yes, I'm bad at mental math this early in the morning, and no one corrected it. Okay, so at the conclusion, what we've now found is we had that shortest distance from New York City to San Francisco, which was New York City to Chicago to Denver to San Fran. And the cost of this path, again, however we've defined cost, maybe this was mileage, was $25.55. Okay? So Dijkstra's algorithm more generally finds the minimum path or the shortest path through a weighted graph. Can you think of other types of problems where maybe we have some sort of weighted graph, we want to know a minimum path? Can you think of others? Some of them are maybe map related, others aren't. But this is a much more general algorithm than just being able to sort of solve a MapQuest type problem. Any ideas? Okay. Well, a couple that I have is, so, you could think about maybe changing the cost function. And so maybe instead of knowing even what's the cost of flying airfare, we're going to look at airfare between different cities. What's the earliest we can get to San Francisco? And so whatever route that we end up choosing through the graph, the only thing that we're using to measure cost is just when do we arrive. Okay, we need to get to San Francisco as quickly as possible. What's yours? Is that a cost function that we can set up and use? Sure. And any path that we have, we can figure out what's the cost associated with that path, and then use that to compare different paths. There's also one in here. How do you think this might relate to solving a Rubik's Cube? Yes, you can use Dijkstra's algorithm to tell you how to solve a Rubik's Cube. Any ideas?
You make each little square of vertices on a graph, and then you put like a distance between each vertices. So like the one right next to it would be like one line.
Okay, so you take all of the nominally 26 cubes, because the one in the center doesn't really do anything, on the Rubik's Cube, and you make them the vertices in the graph, and you can measure the edges and the distances between them. That might work. There's maybe a little bit of an easier way to do this. No, it's a good idea. Okay. One of the ways you can do this is say, well, let's let each vertex of the graph be one possible combination for all of the faces. So there's one particular vertex, maybe our destination, that says one face is red and one face is yellow and one face is white. And so no matter where this thing starts and it's all screwed up and disoriented, we can then have edges saying, well, if there's one move connecting here's a configuration to here's another configuration, draw an edge. And what we're now looking is what's the minimum number of hops that we have to do to get from wherever we started to what is that completely solved orientation. Now, in this case, technically the graph is weighted in a sense. What's the weight on all the edges? Just one. Is there any difference between moving this face versus moving this face versus moving this face? Not really. You just want to know what's the minimum number of twists to get back down to the original. And so you could actually use Dijkstra's algorithm in that sense to solve this problem.
So just to be clear, in this case, when we're talking about because we know the graph is weighted,
Mm-hmm.
Yep.
Yep.
Amount of miles place to place.
Yep.
Wouldn't that mean that pretty much the cost, basically, the weight is?
Yeah, so the weight is exactly reflective of the cost. Yep. That's how we get the weights on the graph, is whatever our cost function is to say, what's the cost of this path? Yep. Okay, so there are a couple interesting related problems that we can see sort of thinking about this a little bit more mathematically. There's a very common problem known as the traveling salesman problem in discrete math, or the TSP, it's sometimes abbreviated, which is a very, very similar question, something of an anachronism in the 21st century, but back in the 1950s and 60s, this is a big deal, where we would say, given a list of cities and different paths that you can take between them, again, nominally interstates, or if you really want to go back to the 1950s, the U.S. highway system that predated the interstates, we have some salesman who lives in Dallas. And this salesman needs to visit Dallas and Oklahoma City and New York City and Boston and Salt Lake City and San Francisco and Los Angeles and Tucson. And we know how to map between all of those different places. What's the shortest path that that salesman can take such that he or she only visits each of those cities once and ends back in Dallas? Because nominally, if that's where his or her house is, where would he or she want to end when they're done with this trip? Back where they started in Dallas. So now you're looking for what's a cycle in the graph that includes all of those cities, all of those vertices, that has then the minimum cost going around the edges. As it turns out, this is actually a very hard problem to solve. How hard is it? XKCD wrote a cartoon about it a few years ago, where the absolute brute force solution, if you try to then go and consider all the different paths, is order n factorial. So if we have n cities on our graph, not even to say we had n cities we want to visit, but the United States has, I don't know how many cities, we represent all of them on the graph. What did we say last unit about an algorithm that scales n factorial? Find a different problem to solve. Okay? So it turns out you can be a little bit more clever and you can eliminate a bit of the redundancy using some of the tricks and things that we've seen, and you can get it down to order n squared 2 to the n. So instead of factorial scaling, we can get it down to something that scales exponentially. Is that still something really good? No, it's better than factorial, but you should still find a better problem to solve. Okay? The joke then is sort of the 21st century makes things fun because you could just sell it on eBay and not have to visit any cities. Order one. And what do we say about constant scaling algorithms? We like them. So while the guy selling on a computer is still working on your route, and, well, sarcastic answer. Okay, so maybe some of the questions now when we're thinking about this as more technology becomes available, can we use it to sort of change the problem? And if something's not working out real well to solve, can we make it easier using that? This is a bit of a joke, but there's a good point behind it. So the last thing I want to talk about today is sort of, what's the math more generally? We've already seen algorithms. We've already seen cost functions. We've already seen graphs and weights and cycles. So what's the new thing that we're bringing to the discussion as we're talking about this route finding in Google Maps? Anybody have any ideas? What's the big math concept involved here? It's optimization. Was that what you were going to say? Sorry, I didn't see your hand up in time. Okay, complexity and optimization. Yep. And so the idea of optimization is selecting the best element with regard to some criteria from some set of available alternatives. So when we're looking at our total map of Google Maps, we can say, well, here is a route from New York City to San Francisco. Here's a different one. We could go down through Dallas and over to Los Angeles and then up to San Francisco. Or we could have gone up to Boston to Chicago to Dallas to Denver to Los Angeles to San Francisco if we really wanted to take the scenic route. But we have all of these possible alternatives, and we want to know from them what's the best. And so it says with regard to some criteria, because is best uniquely defined? No. Use whatever criteria you want to figure out best, and then look at all of the possible ways to do it and choose the one that has either the lowest of those criteria or the highest if you were looking to maximize something. And so the way to think about this is we want to find the shortest, and again, shortest meaning minimum cost, there's that word minimum, from a set of many possible paths. Just as a tip-off, depending on what you're working on or what problems come your way, anytime you see the words most, least, best, worst, maximum, minimum, that list can certainly be expanded, that's usually a dead ringer that you're working on what type of a problem? Optimization. Okay? So let's discuss optimization problems. Where else, besides maybe MapQuest and Google Maps, where else would you see or have you seen optimization problems where you've tried to optimize something? I know you've all done it. Okay, so calculus. We'll come back to that point in a minute. I don't want to say the C word more times than necessary.
Going back to the last section that we were working on, kind of just like how we were trying to selection, so we're trying to figure out what's the decent marker.
Right, so we were looking in the last unit. How do we minimize the number of comparisons to find that minimal cost function for an algorithm? Okay, that was in some sense an optimization problem, absolutely. Because there was that word, find the best algorithm, optimization. Other places? Yeah. Okay, when you go shopping, you're looking for the best price. So maybe you have all your sales flyers, or you go online and try to find coupons to find what's the least amount of money you have to spend to buy, I don't know, I'm guessing green beans and casserole, or cranberry sauce, and maybe some stuffing and some mashed potatoes and a little bit of turkey and other things of that nature right now. Okay, where else have we seen optimization problems? Or have you seen optimization problems? Okay. So logistics and scheduling. How many of you have received a package from UPS or FedEx or the Postal Service? Okay. Why do they care about optimization problems? Because they want to get the package to you the fastest. No, that's giving them way too much altruism. Time is money. They don't want to spend any more time having to deliver this, or cost when gas used to be $4 a gallon. They don't want to spend any more gas than they have to. And so one of the things, there's an interesting link here I would encourage you to read. UPS a couple years ago basically removed something from its driver's routes unless it was absolutely unavoidable. Do you know what that thing was? Left turns. UPS trucks will typically never make a left turn. They found out, because right turns are easier to make, you can make right turns on red. They're a lot easier. You don't have to wait for the special light in the signal. That it was actually cheaper to have a person circle the block and do 3 right turns rather than sit at a light waiting for a left turn. And so they were able to actually do the study and find that was shorter. It required less time. Might require a little bit more gas, but okay, there's a trade-off here. And so UPS trucks typically, unless there's just really no viable alternative, will not make left turns. I'm not making that up. But that's sort of one application of optimization. Another one, manufacturing. I won't ask for a show of hands here, but I'm guessing either you have or you know someone that's been in a major car accident at some point. It's not a fun thing. There's certainly a lot of bad outcomes that can occur. But what is one of the reasons why the fatality rate in a car accident is as low as it is? Because the engineers at Ford or GM or some other car company have spent a lot of time and effort minimizing your risk. So they've designed the car. So there's the picture of the crash test dummy. You've got this car barreling along at 45 miles an hour, and it hits a big wall. As that car sort of crumples and absorbs all of that shock, what happens to it? They've designed the car so that the engine component will take a lot of the blast. It will wrap its way around the cabin, and the trunk in the back of the car hits a lot of that force. But what happens to the cabin? It stays intact as well as possible. Is that by chance? No, they've optimized the car to do that, to make it safer. Cars can be replaced, engines can be replaced. Christmas presents in the trunk can be replaced. You can't. This is not an accident. Well, literally, it is an accident, but okay. Chemistry and nature uses optimization. If you've seen self-assembly, you've all taken probably a biology class and seen like DNA, there's these base pairs and they do all sorts of weird things. That's basically nature saying minimize energy. And these structures will spontaneously form. I don't want to spend a lot of time on this, but this is one place, again, where we've seen optimization. It turns out penguins actually optimize. This is some ongoing research in the Ecology and Evolution department here, where they can actually take drones and go take aerial snapshots of penguins. It's hard to see on the projector here, even on a good day. There's a whole bunch of little black dots speckling this landscape. Each of those black dots is a penguin. And they find these penguins sort of optimize their interactions with each other to make sure like they're close enough that they have protection from predators, but not so close that they're invading each other's personal space. Okay? And it's kind of neat, but you can frame this as a big optimization problem of sort of maximizing my local happiness. Again, you're all sort of packed in like sardines right now. I'm sure you'd much rather have a seat open to your left or your right, but this is the room we're given, so sorry. Okay, so we've got a few more things to say on optimization, but maybe we'll save those for next time. Does anybody have any questions on what we've discussed today before we have our quiz? Okay. Then if not, we will start handing out the quiz. Remember that your term paper is due tonight. Good luck on the quiz. Have a wonderful weekend. And